So we move on to problem 5.57 of Sonntag, in which we have a piston cylinder arrangement which is attached by a spring. The spring constant is given by 15 kN per meter. The initial state contains mass 0.5 kg at saturated vapor, and at a temperature of 120 degrees Celsius. The final pressure because of the heating is P2 equal to 500 kilopascal. If we do a force balance of the spring, the free body diagram, we have the force due to the spring acting downwards, the atmospheric pressure, and suppose we have any random force given by F1. The mass of the piston is acting downwards. All this is balanced by the internal pressure of the piston. Therefore, PA, which is the upward force, is equal to B atmosphere times A plus F1 plus mass times gravity plus K times X minus X0. If you multiply everything by A square and then divide it, I am not going through the detailed calculation steps, but P is equal to C1 plus C2V, where C2 is equal to K by A square. In terms of specific volumes, we can write P is equal to C1 plus Km by A square times V2 minus V1. It is given that the final state is equal to 500 at kilopascal. So we must find how this particular state has evolved. It is linear in volume, that much is clear. So once we know the work done, we can find out the final temperature and the heat transfer in the process. So this is how we do it. State 1 is given as x1 equal to 1 and T1 is equal to 120 degrees Celsius. The mass of the system is 0.5 kilogram. The final pressure is equal to 500 kilopascal. So the specific volume at state 1 is equal to volume steam at T equal to T1 and X equal to X1, because this is saturated water vapor. Okay. So the second state has to be found out through the definition of the slope. So the slope, if you look at this, the slope is equal to P2 minus P1 divided by SP vol 2 minus SP vol 1. So the slope we have already found out is equal to Km by A square. So that is equal to K times M divided by A square, where K is equal to 15 kilonewton per meter, A is equal to 0.05 meter square. So the mass was already found out earlier through this step. So the slope is by definition equal to this. The only unknown in this equation is the specific volume of 2. So once we have the specific volume at 2, we can find out all the other properties by using the fact that the pressure is also known. So the temperature at point 2 is the temperature of steam at P equal to P2 and volume is equal to SP vol 2. Similarly, the heat transfer in the process by means of the first law of thermodynamics is equal to mass into U2 minus U1 plus the work done, which is equal to half multiplied by P2 plus P1 times the mass multiplied by the specific volume 2 minus specific volume at 1. Okay, let's see. Okay, so there's some problem. Let's see. Okay, there seems to be some errors in the definitions. So we have not yet defined what these fellows are. So U1 is equal to the volume, the int energy steam at T equal to T1 and X equal to X1. Similarly, U2 is equal to int energy of steam P equal to P2 and V equal to SP vol 2. Let's see. Okay, there's still a problem. Q1, 2 and T2. So T2. So the area is not, the area is also given. Okay, so the P1 was undefined, so P1 has to be found out. P1 is equal to pressure or steam at T equal to T1 and X equal to X1. Hopefully there's more than one equal to sign. What's wrong? Okay, there was a small typing mistake apparently. So the problem has been solved. It was rather laborious, but the idea is very simple, that the slope has to be matched to find out the specific volume at the point 2. So the amount of heat transfer is equal to 587.6 kilojoule and the final temperature is 803.3 degrees Celsius. So I repeat, the idea is very easy in the sense that the pressure and the volume have a linear relationship. We are given the initial pressure as this, and the initial volume is also found because the point in the PV plane is identified with P1 V1. The slope of the line is equal to Km by A square, and we know that final pressure is at 500 kilopascal. Therefore the second point is also known. Second point is also specified because there is only one point of intersection. Okay, the work done for such a linear process is equal to half times the sum of the initial and final pressure multiplied by the total volume change, and the heat transfer is equal to the addition of the work done to the total change in the internal energy. This is how we were able to solve the problem. Try this out. It's not very different.